Center now for about my 24th year, coming up in May. Anyway, let me give you some background on this. Make sure that this is working. Okay, there we go. Before I go any further into this talk, I want to acknowledge the folks that helped me put this together. The Regional Citizens Advisory Council funded the study, and Jeremy Robita helped with all the outreach. We did every precursor to every experiment. They did that, but we did everything off the end of the Auckland. Dave and Annette Janka, and Dave Rental and Brad Reynolds were crew. Dave Rental also he's the skipper of the Vixen. We used the Vixen as a retrieval boat. And Kirsty Jericho served as my technician for all three experiments. Yeah, a little bit about the history is Scott Powell suggested this in the spring of 2015 to RCAC. They liked the idea, so I took over, wrote up a project design, submitted to them in August. They voted on it in September that year, and then we got funding for 2 years. The past work has been pretty minimal. We had some precursor work with environmental impact studies done by UAF-IMS in the early 70s, and their study on the circulation was comprehensive as they could at the time. They lacked a lot of our modern equipment, so they couldn't really do as much as what I did with this, especially with the drifters and the ADCP work. Following them, Joseph Colonel did moorings in the Narrows in the 80s. He was measuring water exchange between the Sound and Port Valdez, and he found some interesting characteristics of when the pressure gradients move through, particularly low pressure gradients. It can create an imbalance between Port Valdez and Prince William Sound that allows water to come out and then deep water to move in. And I think I've seen now what may drive that. There's a lot of outflow when we have easterly winds, and I think that is what sets up the sea height variations take place, but the winds also cause water to flow out, and that draws deeper water in over the sill. Anyway, so the project's goals were to look at surface and subsurface currents and what conditions physically are driving the circulation, particularly winds, tides, spatial differences in water density, and then we want to look at seasonal variation. The end uses are well spill trajectory modeling. The RCAC said that there's scenarios and contingency plans, which I'm not totally familiar with what they are, sensitive area protection, and the thing that we were most interested in is dispersant usage, because if dispersants were applied to spilled oil inside the port, what would the fate of that oil be? And the dispersants can allow it to be entrained down into the deeper water column. And this program was beginnings of background data that could answer that question. So there's three seasonal experiments. We start in the summer, then the fall, late winter. The conditions in the summer were pretty mild. It was partly sunny, but it was dominated by diurnal sea breezes every day. And in the evenings, the breezes would reverse and sometimes come out of the northeast, but they were light. In the fall, it was cool and wet, obviously. And the winds were initially moderate to light, but they increased periodically through the whole study, and that had a major effect on drifter trajectories. Late winter, cold and very strong winds blowing out. We caught it at the end of one of those katabatic wind periods where it wasn't as extreme as it could be, but it was strong enough that it was consistently blowing out for the first 5 days of our oceanography work. After that, it laid down and got calm, and I saw a whole different set of drifter patterns. So the instruments we used for the oceanography work, we used a CTD, which a lot of you guys are already familiar with that. It's a conductivity, temperature, and depth instrument. We lower it at stations. It gets us the temperature, and the salinity comes from the conductivity and the pressure. But other variables can be derived from the CTD data, and particularly the density through the equation of state. And that is what is of interest because it's the density differences that can drive some of the subsurface flows, as well as a freshwater gradient at the surface can also produce a density difference driving some flows. So the types of drifters we had, this is the total number that we had on hand. There were 29 total, but out of all those drifters, I only put a portion of them out at any one time. The iSpheres are the ones at the surface. Microstars have a 1 meter drogue, and the other two are surface velocity program drifters, or the 10 meter and 40 meter holy sock drogue. So I'm going to go through these guys. Here are the eye spheres, just as their name, they're just a sphere with a flange bolting them together so you can open it up and change the batteries out when you need to. These things were designed really to be put out in the advance of an oil spill. The oil sitting on top of the water like a bubble, and wind is driving the immediate surface current is going to drive that oil and directly move that surface current. It's not the deeper current below, but the very surface. And these guys responded to those types of conditions. They also had a tendency to go aground through wave action or strand on a high tide, like this guy over here. He's over down in the middle of the low river, and he went up on a high tide and he got stuck. These are the microstars, and they've got this nice orthogonal diamond-shaped drogue, and it's very effective in drag in capturing that 1 meter current. In fact, there's such drag in that when you lift it out with a boat hook, it really resists before you finally get it up to the surface, and then it just breaks free. But the little spheres are so small, they have very, very little drag associated with them compared to that drogue. This is a Microstar that came in at the end of the September survey, and it was driven in by these winds out of the low river here. At the very end, we had a bunch of acceleration of wind out of the interior, and it started to move in, and then that wind came in with gusts. And I happened to be out at the pier here at the city dock looking for these things, and I saw a pair of them moving in, and I said, they're going to come into this dock. Oh, man. So what am I going to do to stop them from going under there? I had to watch them as they came up here, bumped into the dock, finally floated out, went around the corner. One of them went aground where I couldn't get it, and the other one I climbed down a ladder with a boat hook and got it and brought it out.
Shelton, are those things tracking with a satellite, or are they recording the lat long?
Oh, they're all GPS transmitting. I didn't mention that. That's it. All of them have GPS.
And through a satellite?
Yep. So these are the SVPs, and the 10 meter guys are right here, and you can't see the drogue very well. It's a big black group here, but it's got 3 of these isospheres sitting on it. So it's about a couple feet in diameter. It's big. But those things have a long, fully socked drogue, and the 40 meter one is so strong when you pull it out, you have to actually pull across the deck on this Nelson wire, and then go back and run over, grab it, pull it, because it's just really hard. There's so much direct resistance those things have. It's amazing. Okay, the design of the oceanography work followed these transects. We did 6 of them here, 5 transects with the zigzags in between. And the letters here stand for the cross fjord transects where we did the CTDs. So in June, I originally had 4 on each end, but I took 1 out on each side for the sake of time. And we got 12 CTDs in every set. We ended up with 6 sets of CTDs over 16 repeat sets of ADCP data. So June, we got quite a bit of data, despite the fact we had shockboard breakage and other things. And in September, same pattern, except I decided to take out these middle ones and put the fourth station back on each of these end transects to get a little bit more cross-fjord resolution. But we ended up with 14 sets of ADCP data and 8 sets of CTDs. Because I took those out of the middle, I got more sets of CTDs this time. So this is an example of the temperature profiles, and that's back at point A, right here, going across these. That's actually this one, right here. So it's these 3 stations right here. And you can see the seasonal thermocline is pretty well developed. It's all the way down to 40 to 50 meters. But there's a conspicuous turning up here. There's an inversion of the temperatures, and that's all associated with cold glacial and alpine runoff into the rivers coming in. Beneath that temperature minimum right here, then it gets very isothermal. This type of profile right here is a very typical fjordic profile in late spring, early summer for almost all fjords I've looked at around the world that develop. The remnant of the cooling in the winter is pushed down in the water column as this new water is warming up. Okay. The salinity profile, it's very shallow. The salinity changes all up in the upper 5 meters or so, and there's just a gradual increase in salinity until we get down to 60 meters, and then it becomes isohaline again. Okay, I'm going to go through some vertical sections across that northern, it's a northern transect that goes from that point A out to point E. Let me go back. So it's going across from this point to here on this north side. Okay, the one thing is you notice right off the bat is that cool surface water in here in the interstations.
Are you at the north right now with your pointer and where it says interbasin? Is that the north end of the transect?
Yeah,
And
yeah,
then,
that's point A, but I was just pointing to you. That's point A, and we're going out. So as we go from the inner basin to the outer basin, you see how rapidly it warms up out here. All the solar heating is hitting here out in the outer basin, and the cooling is taking place because of the runoff. Here's that subsurface temperature minimum that's pretty ubiquitous over the whole fjord.
that's the warm water being forced down.
Cold, it's a
Or, I mean, the cold.
seasonal cooling, yeah, a remnant of that. That's most likely what it is. The salinity, and there's more fresh water in this region in the inner area than there is out in the outer basin. So this is producing a salinity gradient out here. There's not much other gradient at all. And when we look at the, I'm gonna get the hang of this thing. We look at the density. The only real density gradient that's being produced by that fresh water is up here in the upper 5 meters or so. So there's going to be an estuarine dispersal as a result of that moving water out in the basin. If indeed Coriolis turns it, which I'm sure it does, like the low river where it comes out, Coriolis turns that plume northward. And so all of that fresh water joins rivers along and streams on the north side. And so you tend to get a freshwater flow on the north side. It's fairly prominent. But down in the deeper water here, there's no tilting to the density gradient to speak of, nothing that can be really seen at this scale. So there's nothing to really say the density field's driving much flow, that subsurface flow.
It does look, if you look at the yellow color, and it is slightly tilted, the bottom of the yellow,
Very, very little.
between like 20 and 10 meters or something.
Well, wait till you see.
See, it's like 20 meters on the left, and it's about halfway up on the right.
It's very slight. So when we get to September, you'll see it a lot more pronounced. So yeah, if there is some baroclinic flow being driven by the density field, it's pretty minor. There's not going to be much of a pressure gradient associated with it. Okay, it's an example of the ADCP data, and this is east-west velocities of the U component of the flow across one set of transects when we came in. I think this is a flood tide, and this is the north-south. And when I mentioned the baroclinic currents, the ADCP picks that up. You see that the pressure gradient over depth driving the flow is not uniform, so that creates a baroclinic flow. A tide wave that's moving in with no other factors affecting it will have an even pressure gradient through the whole water column.
Can you move that? We're not seeing the scale on the right side. Or is that cut off?
Oh, it got cut off.
So is one negative and one positive?
The blue is negative.
Okay.
And the other's
So it's
positive.
direction then.
So why the projector's cutting that off, because I'm pretty sure that was on my slide. But anyway, let's go. These are negative, so since this is an east-west velocity, that's west flow moving out. It's on the north side. It's a pretty strong flow moving out. And here on the north-south velocities, this is a flow moving north. Okay, so this gives a better picture spatially of what you just saw there of those components. That's that north flow coming out on the flood tide. But it all comes out on this side over here, and there's a flow moving in here, but it turns cyclonically, counterclockwise, outward. There's a lot of flow variation here at 11 meters, which is the 8-meter depth in the first depth bin of the ADCP from 7 to 15 meters. These numbers that I have are the midpoints of those depth bins.
So do people that go back and forth in there corroborate that conclusion, Dave? You've been in Port Valdez so many times. You could like ride the current going out on the north side.
If you're very, very patient.
Yeah. So beneath that layer, let's see, a 19-meter layer, okay, there's that cyclonic flow that's still going out beneath that, and that showed up in the cross sections of the ABCP data, but notice how low the currents are in the fjord of that. They're very light.
It's probably handy for the tankers if there's not that much current in that.
No, see, it drops off even more down at 27 meters. These currents were like 7 centimeters a second or less. So like you were saying before, there's just very minimal tidal flow at this time of the year anyways, in June. And then beneath that layer, very low currents. They're flood tide, so they're mostly moving in under that other layer, which had a lot of variability to it. So what happens when you get layers moving in different directions, the tide's coming in and creating a volume change, and that's the maximum amount you can have in there at any given point in time. If you start moving water from one area to another, you've got to replace it somewhere. The conservation of mass, what we call continuity of volume, will create a flow elsewhere when you've got an acceleration somewhere else. So a lot of currents just get driven just by that alone.
Could you run through these depth things, starting at the surface again and go down to 43 meters? Yes.
I think that's, okay, that's the, oops. That's the first bin.
Okay.
Okay, so you see the flow on this transect and this one turning.
Right there,
Yeah, it's an eddy, it's a cyclonic eddy, and the drifters, the 10-meter drifters showed this really nicely, especially in September.
So if there's an eddy there, do you get any entrapment and junk on the surface in the middle of this Port Valdez right there?
Couldn't say, we couldn't
Yeah.
really see for sure because the
But
wind.
that's something to consider, not only for dispersants, but for collision with items.
Well, the problem is
Yeah.
that the winds were blowing down a lot.
Okay.
This is wind wave action from those diurnal sea breezes. So this is subsurface, so we couldn't see. I don't even know if this is expressed at the surface. It only showed up in the 10-meter drifters. It did not show up at the surface. So I suspect what happens is when the winds die down, you don't have that forcing, this type of circulation can set up. It's not a closed geostrophic circulation where the pressure is being balanced with Coriolis so that you have a low pressure center here that's driving around it. It's an eddy being driven by turbulence, large scale turbulence of the system. Because it's ephemeral, it comes and goes, and it typically shows up on ebb tides. So you'd have to have a density gradient across both ways orthogonally to actually have this set up as a density driven, geostrophically balanced type flow. That just doesn't happen in here. A lot of these flows are just large scale features of turbulence in the fjord system. I'm fairly confident.
Well, what you mentioned earlier about that, where when you change the volume in one place, well, how did you say that? You change the volume in one place, you create a flow somewhere else to compensate? Or
Think of it this way, if you've got water moving two directions away, like a divergence, because the water's incompressible, you're gonna have to draw water up to replace that water that's moving away. That if your water's moving together and one flows underneath the other, same thing. You're gonna have to, because that water's moving, something's gotta replace it. So circulation can be driven just because of one current in one area that's imbalanced elsewhere, draws water hydrodynamically into that area because it's moving water out, so water has to come in and replace it. It's just a property of conservation of mass.
I got it.
That's the way it works, yeah. It's one of our equations, in fact, that we use out of 7 that drives circulation models, the continuity equation. It takes conservation of mass, and you can get rid of the density out of it and just go straight with flow. And then there's like 6 other type of equations. 3 of them are the momentums, and the others are just diffusivities and the equation of state. And there's 7 unknowns and 7 equations, so theoretically they can solve them, but you can only do it with a computer. Numerically, you can solve the intervals. You can't do it any other way. All right, so before I show the drifter animations, I want to talk a little bit about the winds that we experienced in June, and these are those diurnal sea breezes. You see at the beginning of the experiment, they were very strong, and they dropped off for a while, and they're kind of moderate, and eventually at the end of the experiment, they picked up again. But also in between those westerly winds coming in, at night, we had northerly, northeasterly winds, very light winds. But a lot of times you can see that the vectors are coming from the north-northeast. Those light winds definitely pushed ice spheres and microstars to the south side of the fjord. All right. Okay, I got to come back here to drive this thing. Can't click the image with the clicker here. Okay, so what I'm going to show first of all is the ice spheres moving on, it's the June 23rd to the 27th, and there's 3 of them, and they're launched at those periods in the winds, relative to the winds. So 2 of them were released right at the peak of those diurnal winds, and one, the last one, 460, was when there was a lull. So the first one was driven inward by the wind, and then it exited. So it exited the fjord in the night, but then when this wind hit here, I'm pretty sure that drove it back up through the Narrows, and it came back up into the port. So it continues. Come on. Uh-oh. Why don't you want to continue? There it goes. And it stayed right up around Mineral Creek. Now that one right there was also driven in by this wind right here. That drifter was driven in by this wind here. But it went down towards the low river. Okay, now it came back out, and then the other drifter took off, one with the magenta pluses, and it started moving. So with the diurnal winds, these guys would move into the fjord, and at night they'd move back out, and what we ended up with is this back and forth crisscross pattern in the flow. So you see with these diurnal winds, material would get moved in and then try to come back out in the evenings or night and then move right back in the next day. It's not often that it actually exited the system. Now, that wasn't the case in September. You'll see when we get to that. Okay, these are the microstars, and they follow a very similar pattern. Just not, they don't go as far out as the other ones before turning. This guy here went all the way out towards Chute Bay and turned back. But one of them went right to the same area where that ice sphere went, turned back again. So they're being driven by the wind in a similar manner, but they're deeper in the water column, so it's not exactly the same. Because they're getting the current, whereas the ice sphere is getting the direct wind as well. So they follow different trajectories.
How deep is the drone on these guys?
About 3.5 feet,
Okay.
1 meter. They were those diamond shaped,
okay.
diamond shaped guys.
Yeah.
So finally, one of those microstars tried to get out, and we grabbed it down there. As you can see, they just back and forth, but they do travel up, back and forth across the breadth of the whole port, which is really, it's interesting how they do that. Okay.
Shelton, I have a suggestion, is when you show these graphs, is have a little tiny photograph of the microstar and like put it in the corner somewhere.
Oh yeah, good
So that
idea.
people could remember which one was which.
That's a good idea. This is the first cut at doing these things. I mean, it took me a lot of work just to get the data in shape, just to capture the frames. Okay, so here's the SVPs. And this is going to take a little longer because this goes through the whole deployment period.
Those are the real long ones?
Yeah, these are the guys that are down at 10 meters depth for the Holy Sock drone. So that's a good idea. I can put that picture of those too.
So these guys, there'd be no wind effect whatsoever.
Not generally, but I'm not convinced now that those strong periods of those sea breezes don't get down that deep. Because if you watch these guys, there's periods when they suddenly turn and they'll start moving in. And I think that that's not just tide. That maybe that wind and also it can be synergistic with tide. You know, if it's in phase with the flood tide and that's blowing in, it can definitely give them a kick.
Okay.
So here's this one. See this one going in like that? That's pretty rapid. Now it starts to follow a boundary along there, almost like a boundary current, and it comes back around.
So the second ones that you deployed every time, were they all deployed at the same time, like every type of?
No, that at first we put singles in it first, and then I started doing experiments with groups of them. And
Because I'm just noticing every time the second drifter that goes in always goes to that back corner. I'm wondering if you put it in at the same time period when the currents and the winds were all the same across all the different drugs.
in this particular time, I can't remember for sure. They may have. It definitely did the same pattern as the Microstar and the iSpheres for that particular drifter.
So you
But-
didn't like put them in the water one after the other?
Yeah, we usually
You
did.
did. So you were putting them in at the same time? But, like,
They should. I usually put in groups
Okay.
to the same spot. So that I'd have to go back and double check with that SVP went in with one of that
We
iSphere.
we put in a group of surface, 1 meter, 10 meter,
yeah.
all at the same time.
Yeah.
So
Yes,
it's 2 or
that's what
3.
you're
Yeah,
asking.
That's
Yes.
what I was
Yeah.
asking.
Yeah.
Also, so another
Here's- okay.
suggestion, Shelton, would be to have like a time thing running. I don't know if you can do it with the graphic.
Well, that's a
You've gotta-
great
You've got to have
Series there.
a timeline running somewhere in
Yep.
the graph.
Yeah, I know that stuff, Tom. I just didn't.
It might overwhelm the.
I didn't have time to do it.
Okay.
That's all. I'm going to put tides on there and winds. I
So
just,
the timeline is more important because when you're showing these sequences, we could see that, you can see where the dots moving across the timeline, and so if you're showing different drifters and we're going back and doing the same time, people can then pick that up real quickly.
okay. Well, like I said, this is just to show the patterns in general right now. I did not have time to put all that stuff in. But let's talk about that later. I want to get your suggestions. So yeah, this is that cyclonic flow that the AECP picked up, but this drifter didn't pick it up until it was put right in the spot where those flows were taking place. And there seemed to have been a break between those flows in this region of the fjord here and this inner basin as well. And I'm hoping I can get to the bottom of why that takes place. Come on. Come on. Jeez, isn't it funny, right on my computer at home, I just click it and it goes.
It could be the talking to the projector. Is that a USB 2? It might be just too slow for the data that you're trying to push.
I don't know, it worked last night.
Oh.
There it goes. Okay, so it was redeployed with you see those lines. So again, it tried to make the cyclonic turn, but now they don't make that. They turn back in, and that's what makes me suspect that the diurnal winds do get down to 10 meters on these guys. So we're at 28 to July, June 28th to July 1st now. And that one definitely appears to follow a current out that north shore. I redeployed it, and it tried to do the cyclonic turn again, but it's going to turn back into the port.
Is there a reason why you redeployed it?
Yeah, because it's already out there at Chute Bay, and I didn't want it to go any further, so I didn't have to go grab it. Okay, so let's go into September now. Okay, here's an example of the hydrography, and that's across those 3 cross-fjord transects that I showed you. I took the ones in the towards the middle out. I just did 3 sets. But there's 4 on each one. But interestingly enough, there's a lot of similarity to the profiles and the temperature, but you can see a change in the thickness of this thermostat. And a thermostat is an area where you have a mixed layer sandwiched in between other layers. And so that's likely there was a period of mixing that took place before we got out there for our survey. The other thing that you'll notice is that the
You wanna go to some of the-
Oh, I you gotta photograph this stuff. I get it. Okay. So there's cold water up here at the surface, but that's not just all freshwater input. It's not all freshwater input. It's surface cooling in September as well. Okay, here's the salinity profiles. You can see the freshwater mixed down much deeper in the water column, and there's a quasi-halostat in here too, where this has been mixed. Okay, here are the vertical sections, and again, we're doing the same thing. We're going from the inner fjord outward. So you can see where there's more fresh water at the surface in the inner part of the fjord, and there's less as we go farther out. Here's that thick halostat. And here is the salinity gradient, and there is a bit of a surface salinity gradient, but it's not as extreme as in June. But as I was mentioning to Tom, the salinity does change. There's more of a tilt to the salinity surfaces, and that shows up in the density surface in particular. So you can see the definite tilt to the density surface. So there may be something going on with the fresh water at the surface as well as the subsurface density field driving more flows. And the flows were much stronger in September at depth. In fact, they were double the magnitudes that we got in June. So this is an example of just the east-west currents for a flood tide and an ebb tide. And we're going from the outer bank transect, so we go north to south, across, and back and forth, and we go in. So this is on the north side. This is all on the south side where you see this positive number. That's an inflow, and it's getting up to 35 centimeters a second, so that's more than double what we saw in June. Now, as we went in, we transited into an ebb tide, and that's what's going on here. You start to see a reversal taking place under that layer. During and near the ebb tide, as we go back out from the inner fjord to the outer fjord, it strengthens. And then you start to get these really strong cyclonic cells. Okay, so 7 to 15 meters, you don't see it there on the flood tide, just because we're going in, transiting between the flood and the ebb. But there's the strong flow in the south that's coming in. Okay, the strong flow still in the south coming in on the flood tide. Then it starts to change as we get down to 21 to 31 meters, and you start to see a turning in these flows. There's a reversal coming back here. You have to remember that these things are changing in time as we're going through. So when we see this reversal here, I don't know for certain if that flow is still in place, but what would be suggested by it is there's some sort of convergence going on right in this region of the fjord that I was talking about before, where flows come together. And then beneath that, there's the ebb tide going out. Okay. Now, on the ebb tide, there's that strong cyclonic circulation. And now we can actually see it close right in the center here. So this is a really nice example of that type of flow. Flows moving in the south side of the fjord this way, there's flow moving out over here. So likely what happens is you get these imbalances across the fjord creating shear. And when you have that kind of shear, you can start developing this kind of circulation in the middle. It's just a feature of the flow, not the density field, but a feature of the flow itself. We see it now at 15 to 23 meters, and just a remnant here, very little of it, but the flow is definitely going out to the north side. And a lot of my drifters went to that side and they just shot, when the wind and the tide and estuarine flow were in sync with each other, these things would accelerate out this side. So below that, everything's just ebbing straight out. Okay, the winds during this period. We started out, as I said, with some moderate westerly winds that dropped off for a while, but they're still coming from the west. And suddenly it turned, and we got some fairly strong winds from the east-northeast, going back out. Following that, light and variable winds through most of this period, till we get to some westerlies again here and here, light winds, and then here's where the winds picked up out of the low river. And we got a lot of, looks like it started out from the low river and then started going up from the northeast. This was the wind that drove those microstars up there to the city dock when I was watching them come in. Okay, start this one up. So these are going to be the animations for iSpheres and Microstars and SVPs for September.
It's not an Apple product either. Ice, forget it.
So those guys there that, just to pause for a second, but these iSpheres that went out and suddenly then turned down here to the shore, that's when those west winds started blowing in fairly strong. So they were moving out, but they were pushed by that wind southward, and so they all grounded right down there by Entrance Island. Now these guys left the entire port and went down by Green Island, a pair of iSpheres. One of them stayed there. Dave picked him up later on his way out. And 600 went all the way down to Montague Strait, turned back north. And why aren't you continuing? He actually went all the way to Green Island. I don't know why it stopped. Come on. There it goes. Well, if you're going to get glitches, it's always got to be in the presentation.
Mm-hmm.
So it hung around the west side of Green Island for a while. It couldn't escape there. And then finally it came back southward and went around the tip of the island. And eventually it goes around and grounds. And Rob Campbell picked it up then. And they went out the New Wave on one of their cruises.
You put money on it going to Seward, but
Oh,
double back.
man, we were hoping.
So,
Yeah, Scott and I were hoping to see it head out to the Gulf, but it had other plans. Okay. Okay, so here we have the Microstars. And they'll go all the way through, I think, to the 27th. But notice how they all went out towards the Narrows. Come on. These guys didn't go along that north shore again, but when they get down here, they disperse. So this real dispersion that I saw throughout this whole experiment, particularly in the surface or near surface layer, was whenever a current reached the boundary and couldn't go anywhere, had to move one way or the other, and these guys would then end up dispersing. The iSpheres did it in June. They went up in the duck flats and dispersed all through there. So that's a sensitive area right there if there's ever a spill of oil in the summer with those diurnal sea breezes. Okay. Those guys got forced southward. Every time these shift, there's a new deployment. You're not done. I know you're not done. There it goes. Notice that when it went out that north shore again? These guys are all going out. So everything in September had the tendency to want to move outward. And sometimes disperse. These guys are going all along that south shore. Okay. Okay. Now, let's watch the SVPs. So they went in initially, now he's going to start doing the cyclonic loops, both of them in pairs. And that was the other really interesting thing. They didn't disperse very often. This was an unusual thing for those two to go apart from one another like they did. All these pairs of drifters are mostly just staying on top of one another. And occasionally then they'll disperse. So there were times when there was not much wind and they didn't do a thing, but these guys are definitely getting hit by winds in September. They're also being moved by a subsurface flow as well because of that baroclinic flow. Okay, I think that takes care of those. Now, the 40-meter drifters, they also responded much more dramatically in September because those currents were getting very deep in the water column. I mean, they moved all the way out into the outer basin, and they did some cyclonic loops as well. But what happened at the end when we got those winds blowing out of the low river and then finally out of the northeast, that wind first drove these guys all the way up along the shore, and that's where they ended up grounding. They weren't like grounded on shore because they're so deep. They're 127 feet down in the water column from the bottom of the drogue.
But once the bottom touches it,
That's it. It's caught. It's anchored. So the March experiment, I'm only going to show a couple of things in that. It was cold and very windy, and here are the winds, characterized by there's up to 20 knot winds blowing every day for the whole 5 days that we were doing the oceanography work. And
it was gusting to almost 30 now.
some of it right there, you know, the winds themselves were 20 or above the whole time. But this pattern right here was right, the ice river deployed right during this wind, and it took less than about 5 hours and they were aground. Just shot right over there. The deployment here, when the winds were relaxed, it took them more like about 10 to 13 hours to move across to the south shore. But the winds are blowing from the northeast here, and that seems to bring them all the way right down here from the release points right down to this shore.
This way of presenting the data is pretty nice because you get the time context.
Yeah, take your suggestions when we're done here to
Yeah.
improve this for AGU. So the Microstars, same thing. They immediately were pushed by these winds right to the north shore, but instead of grounding, they followed right along the shoreline and it ended up out here. And then at the period of low winds, they take some little inertial loops here. And what happens with that, you've got a flow moving one way, it slows down. Coriolis wants to make it turn, so it turns anticyclonically to the right. Then another force gets it and makes it move immediately, so it makes these little curlicues basically what they are. A true inertial current will actually make a big circle if nothing else is affecting it once the forcings die down and it's moving under its own inertia.
How did you choose your deployment location?
Well, I wanted to go to different points in the transect where we had the ADCP currents. That was the first thing. But then I decided to test other port areas of the fjord just because it's obvious that the currents take off different directions depending on where you are in the fjord. The main thing was to try to put groups of drifters out. And this experiment, we put every deployment was with groups, so we had good repeats. But you notice how they follow each other so closely. Statistically, I don't need more than a couple of them. It was nice getting a bunch of them together and seeing dispersal along the shoreline, though. So anyway, that's what happens in the Microstars. They get more lazy. They meander more when the winds were down. Okay, SVPs. Yes, these are the SVPs, and they did the same thing. See, that wind-driven current is all the way down. It's actually all the way down below 40 meters. So everything just being forced up to this north shore, even down at 10 meters. Then when I put them back in here for the low winds, they meandered around a lot, but they eventually did go back over to the shore. So I don't know if this was an estuarine flow over here doing this or not. I doubt it. I think it's just an outfjord flow that's consistently going on during this experiment. The 40-meter drifters, same thing. When the east winds, they gradually work their way down that north shore. So what does this suggest? If oil's ever spilled during this time and it gets out in this area of the fjord, this whole north shore is just in danger of being oiled. Then when the winds speeds drop, again, they start to meander much more. And if I was able to get it after the 29th, they probably might have made a cyclonic loop back into the fjord. So this last slide is actually the very end of the experiment. And you can see the winds were very weak, almost nothing, but they're out of the northeast. And then they start to accelerate from the west. And finally, at the very end, we get some decent winds coming in from the west. So when you don't have much in the way of winds, both the Microstars and the SDP start this cyclonic circulation again in the outer fjord. And then the wind kicks them in, they start moving in. Those are the Microstars, those are the ice spheres that came in right there. So I won't go through too much of a summary. You guys saw a lot of stuff here, but in general, we saw the winds were dominated in June by that diurnal pattern and daily sea breezes. The currents were very weak, only maximum of 10 to 15 centimeters a second, and that's about what you get with the general oceanic flow rate. So the strongest flow is at the surface, as we saw, but below that, the deeper water columns, less than 7 centimeters per second. The winds were the main drivers, but they didn't seem to affect the lower layers, because they were blowing for a long time. But I'm not so sure that that's true. I think that 10 meters there may be more wind effects than I originally thought. And the solar heating was creating thermoclines pretty deep, but it's on the top of that, the freshwater input was cooling the inner basin water. The tracks, of course, they're highly varied due to a combination of these three factors: the winds interacting with the tides and the estuarine dispersal. And also, if there's some subsurface paraclinic flow from the density field, that's a fourth factor, but it really wasn't that prominent in June. The surface ice spheres and the Microstars are obviously the most active and were affected by those winds. But if there's no wind, the other factors drove them around. And they kept them inside the port, but it did move them around a lot. The 10-meter SVPs, they're the ones that possibly move with baroclinic currents. And they showed those counterclockwise rotations that the AECP data picked up. And the 40-meter SVP did not move hardly at all. It just sat in the inner basin, went back and forth a little bit, back and forth, very little bit. And finally, when the wind was blowing in at the end, it started moving towards the east side. So the wind, after blowing for 2 days, might have gotten down to that drifter. Maybe. Summer in the fall, currents are much stronger in the upper 50 meters, and we doubled the speeds, 25 to 30 centimeters a second. The deep currents are still slow, less than 10 centimeters a second. The winds, again, major drivers of the currents in the upper layers, but the winds did not seem to affect the lower layers unless they were blowing again for a long period of time. The thermocline's much deeper now in comparison to June, and the inversions are there, but it's due to both cooling temperature, colder air temperatures as well as cold water coming in. And then we saw those thermostats and that quasi-halostat form from some mixing. The drifter tracks, they're highly varied over the depth, and again for different combinations of those forcing factors. And the ice spheres and Microstars were very active, and they all wanted to move outward throughout most of the experiment. And then the 10-meter SVPs, they followed those cyclonic loops very, very nicely. The 40-meter SVPs also showed much more motion, and they moved all the way out to the outer part of the fjord and back in. They also followed some cyclonic cells, and they were affected by winds through near the end. That's when those 40-meter drifters were moved to the north shore and they stranded. So we already talked about March, so I won't do a summary on that. So if you guys have any more questions, I'll be glad to answer them.
I got kind of a quick one, just for myself to get kind of a feel for this. Okay, if we take the velocity of the current, and at the bottom of the fjord, let's say 100 meters, if it's that deep, the velocity is pretty much zero.
You hit at the boundary, the very bottom boundary.
Yeah, and, you know, at the base, it would be zero.
Mhm.
And then at the top, at the surface, you got like maximum flow, let's say. There's no wind, it's just current, just tidal flow. If you had to take and describe the curve from the surface to the bottom, what type of equation? Would it be a logarithmic, arithmetic? I mean, how would it, how does it vary, I guess?
Oh, it would show, well, it depends. If there's nothing else forcing that flow through the water column, it's barotropic, so that the flows are even through the depth. You won't see, but you'll see a gradient that comes straight down until you get to the bottom where friction begins to interfere with it,
Okay.
and then it becomes exponential.
And there's an exponential fall off of
Yeah,
velocity.
and then what else happens,
Uh-huh.
because of the drag of the friction, Coriolis doesn't have as much effect, it turns back the other way, it turns. So wind-driven current will typically turn with Coriolis over depth. Tide, just a pure tide with nothing else driving it, is gonna be going in and out. That's what
It's
you
just
expect
a
to see.
linear being.
Right, you expect to see a barotropic wave going in and out, rising up and down. right?
And it's not till the very bottom that the
For friction.
jumps in there.
But that's not what we see, because we have all these other factors, the density field interaction, the fresh water, the winds, all of those things, then the tide interacts with that, and you start to see all these multiple layers. We call them modes, baroclinic modes. And so if you've got two flows doing like this, you have two baroclinic modes, 3 modes, and so forth. I see many multiple modes. And through a continuous density gradient where it's not a sudden change, or a very dramatic change, where it's continuous, you can have infinite modes baroclinically through that gradient. Anybody else have a question?